Hi everyone, my name is Sam Gross. I work at Meta on free-threaded Python, and I'm a Python core developer. So I'm going to give the first half of this talk on free-threaded Python, and then Neil's going to give the second half of the talk on Pyrefly. Free-threaded Python is an experimental build of CPython that allows multiple threads to interact with the Python interpreter in parallel. This effort was formerly called the No-GIL project, but when Python Steering Council accepted PEP 703, the Python enhancement proposal for this change, the name was changed to free threading. Historically, Python has had a global interpreter lock, which ensures that only one thread can run Python code at a time. The global interpreter lock was added together with support for threads in 1992, shortly after the first public release of Python. From a technical perspective, the global interpreter lock made sense for a few reasons. First, it's really simple to implement. It doesn't require a lot of code. Second, the global interpreter lock is really efficient for single-threaded code. The lock is only rarely touched, so it doesn't substantially affect performance if you only use one thread. And third, the global interpreter lock avoids a lot of the potential deadlock hazards of using multiple fine-grained locks. In particular, the locking discipline of the GIL, or global interpreter lock, is pretty straightforward. You need to acquire the GIL before calling into Python, and you should release the GIL before calling any operation that might block the thread. And finally, the global interpreter lock still allows for some amount of parallelism. C extensions can release the lock around long-running pieces of code that don't access Python objects. But we're now over 30 years since the introduction of threads to Python, and the computer hardware landscape's changed substantially. Multi-core processors are common on desktops, laptops, and even phones. In server environments, it's common to see computers with dozens of CPU cores or even hundreds. Especially as core counts increase, it's difficult to take advantage of multi-core parallelism from Python due to the global interpreter lock. By allowing multiple threads to run at the same time, the free-threaded Python makes it easier to take full advantage of the performance of multi-core CPUs. This is a chart from Kumar Aditya's Async I/O TCP performance benchmark on a 12-core CPU. The free-threaded build is in the blue lines, and the default GIL-enabled build is in green. And you can see that even with the global interpreter lock enabled, there's still some benefit to using multiple threads because the global interpreter lock is released around I/O operations. But the performance is much better with the free-threaded build. This is just a single example, but I think it's representative of the kinds of speed up you can see with free threading. This wasn't the first attempt to remove CPython's global interpreter lock. I'm aware of at least 4 previous substantial efforts, and maybe there are more depending on how you count them. I'm not going to have time to go into them into detail, but I wanted to acknowledge them, especially Larry's work on the gilectomy, which I was most familiar with when I started on this project. I started working on this in 2019. At that point, it was basically a research project. It came out of frustration I had from working on PyTorch and the time that I spent and my coworkers spent working around the global interpreter lock, both in PyTorch and other machine learning research projects. The first public release of sort of the no-GIL effort was in 2021. I think it received a mixed reaction. There was a bunch of excitement about removing the GIL, but there was also a good deal of trepidation about what a change would entail for the Python community and long-term maintenance of CPython. It took about 2 years for me to draft a Python enhancement proposal and for it to be finally accepted in October 2023. The first release of CPython with optional free threading support was 3.13, which was released last October, and we've just released the first beta of Python 3.14, which substantially improves performance of the free threading build. I also want to recognize a number of people who made significant contributions to this project, including my colleagues at Meta and Quantsite, a number of Python core developers, and many volunteers who contributed patches, bug reports, improved performance and testing, and worked on CAPI extension compatibility. I think of the free threading project as having 3 main components. The first is the work to make the CPython internals thread safe without the GIL, without compromising performance. This is a big component with many pieces, and I'm going to talk about it a bit more. The second is an effort to make sure there's sufficient breadth of knowledge across the Python core developer community so that Python, including free threading, can continue to be supported by Python's core developers. And then the third component is work on the Python ecosystem, especially CAPI extensions, which often require at least some changes to work with free threading. The ecosystem is really important, but I'm not going to spend much time talking about it. Instead, I'm going to plug Lissandros and Nathan's talk tomorrow on unraveling community support for free-threaded Python. Lissandros and Nathan and their colleagues at Quantsite have done tremendous work on the ecosystem support, and if you're interested in this, you should definitely attend the talk tomorrow. Removing the global interpreter lock required pretty substantial changes to CPython's implementation. I think of these changes as falling into three broad categories. The first is reference counting. CPython uses reference counting in addition to a tracing garbage collector to free the memory associated with Python objects when they're no longer needed. Reference counting is conceptually simple. Each Python object has an internal counter, and the number of that records the number of objects that refer to it. When the counter reaches 0, the object can be freed. The second category is collection thread safety. This includes things like dictionary sets and lists that are mutable. They can be modified and concurrently accessed by multiple threads. Ensuring that the interpreter doesn't crash when a dictionary list is concurrently modified is one of the challenges dealt with by this project. Some of the same techniques are also used for dealing with modules with mutable state. I think of other things as sort of falling into a broad interpreter internals category. A lot of these subsystems required small changes. However, the garbage collector required a new implementation, and a few things like the specializing interpreter required their own techniques, like a per-thread code array. Reference counting is used extensively within CPython. As I mentioned before, it's conceptually simple. The implementation is also pretty simple and efficient with the global interpreter lock, just a single counter associated with each object. However, reference counting poses a number of challenges for free threading. The first is that plain reference counting isn't thread safe. Using atomic operations to modify the reference count is thread safe, but atomic instructions are a bit more expensive. In many contexts, this might not matter, but reference counting is used so extensively in CPython that the additional overhead would substantially affect single-threaded performance. The second issue is that reference counting can introduce scaling bottlenecks that wouldn't otherwise exist. When two threads access the same object, even if they don't modify that object, they still need to increment the reference count of the object for the duration of the access. This modification of the reference count field for multiple cores at the same time leads to poor performance because the cache line storing that reference count field needs to be sent to whichever core is modifying the reference count last, and the copies on other cores need to be invalidated due to the modification. The problem here, to be clear, is the modification. It's efficient to read memory for multiple CPU cores simultaneously. That scales well, but it's not efficient to modify the same memory address concurrently for multiple CPU cores. The first technique used in this project to address thread safety in single-thread performance is biased reference counting. Biased reference counting works by splitting the reference count field into two parts, as well as storing the ID of the thread that created the object. The first part of the reference count field stores the local reference count. The thread that created the object uses plain, non-atomic operations to modify the local reference count field. The second field stores the shared reference count. Other threads modify the shared reference count field using atomic instructions. The true reference count is the sum of these two fields. Because most objects are only accessed by one thread, even in multi-threaded code, this technique avoids most atomic operations while maintaining thread safety. Biased reference counting improves single-threaded performance by generally avoiding expensive atomic operations, but it doesn't really help with multi-threaded scaling issues that are posed by reference counting. We use a number of techniques for addressing multi-threaded scaling, but the basic idea is to avoid modifying the reference count field for objects that are frequently shared across threads. The first technique is immortalization. Some objects like true, false, and none have a fixed reference count that's never modified. These objects are statically allocated by the interpreter and never freed. And this scales well because we only ever need to read the reference count field. We never need to modify it. And this technique exists in both the default GIL-enabled build of CPython as well as the free-threaded build. The second technique is deferred reference counting. Deferred reference counting skips the reference count operations to objects as they're pushed to and popped from the interpreter stack. Other operations like assignments to dictionaries or lists use normal reference counting behavior. This works well for things like functions, methods, and type objects because they're frequently pushed to and popped from the interpreter stack when calling functions, but infrequently assigned to other objects. Kenjin did most of the work here on implementing deferred reference counting in Python 3.14. And finally, starting in 3.14, we're able to eliminate most of the reference count modifications using static analysis during bytecode compilation. This work was done by Matt Page in 3.14 as well, and helps with both single-threaded performance and multi-threaded scaling. It also applies to the default GIL-enabled build and improve single-threaded performance there as well. Now that I've talked a bit about reference counting techniques, I want to move on to collection thread safety. Again, this is how things like dictionaries, lists, and sets handle concurrent accesses. Dictionaries are particularly important because they're widely used in Python, including for storing object attributes and module-level global variables. The free-threaded project uses per-instance locks for protecting collections like dictionary and list. These are lightweight locks that take up just 1 byte in each object's header. The implementation is based on the design of the locks used in WebKit, the browser engine for Safari. On modern hardware, the locks are pretty fast to acquire and release as long as they're not contended. That is, as long as we don't have multiple threads trying to access or modify the same object at the same time. One of the challenges with introducing locks in general to collection types is you have to be careful to avoid introducing deadlocks. The basic idea here is so we use a new API that we introduced called Python Critical Sections, and the basic idea here is to implicitly release the locks at any places where we would implicitly release the global interpreter lock. We don't do this for all types of locks, just for the per-object locks managed by the Critical Section API. This API completely avoids lock ordering deadlocks, which makes it much easier to add them to existing code, especially since there are no ops in the default GIL-enabled build. The trade-off here is that the places where they're implicitly releasing the locks is a bit strange and makes them a bit harder to reason about. But that's true of the global interpreter lock as well. The API is useful in CPython for protecting mutable state in modules as well as in CAPI extensions. Python 3.13 was released last October and was the first official version of CPython that included experimental support for free-threading. Most of the major features for free-threading were implemented in 3.13, and the code generally, multi-threaded code generally scales well. However, there's few hacks in 3.13 due to the limited implementation time before the first release. The first is that deferred reference counting wasn't fully implemented, so some objects were marked as immortal when they really shouldn't be. In other words, some objects are never freed by the interpreter, and you can end up leaking memory if you create lots of top-level functions dynamically. The second is that the specializing interpreter was disabled in the 3.13 free-threaded build. The specializing interpreter is responsible for a lot of the performance improvements from Python 3.10 and onwards, so disabling it meant that the 3.13 free-threaded build was about 40% slower than the default GIL-enabled 3.13 build on single-threaded tasks like the PyPerformance benchmark. The first beta release of Python 3.14 was released just last week. The free-threaded build has much better single-threaded performance now. The specializing interpreter is enabled, and it works by having separate copies of the bytecode array per thread in the free-threaded build. The garbage collector performance has also improved. Neil Schemenauer implemented stack scanning to reduce the amount of work typically done by the GC, as well as implemented memory prefetching, an idea taken from OCaml, which also improves performance a bit. We've also gotten rid of the temporary immortalization hacks in 3.13 with a proper implementation of deferred reference counting, which was implemented by Ken Jin. We fixed a number of thread safety bugs. Many of those were backported to 3.13. Overall, I think the 3.14 free-threaded build is in a really good state, and we're pretty confident in its design. Going back to single-threaded performance, the criteria from the Steering Council's conditional acceptance of PEP 703 was that the worst-case performance was going to be in the 10 to 15% range. We're generally less than 10% slower on the Pyperformance single-threaded benchmark than the 3.14 GIL-enabled build. Especially on Linux and Windows, on Intel CPUs, performance is about 8% slower. But that means that performance of the 3.14 free-threaded build is faster than the GIL-enabled default 3.12 build and pretty close to 3.13's GIL-enabled build. For some reason, macOS performance on ARM64 is very close to the GIL-enabled build, just 1 to 1.5% slower, but I'm not 100% sure why yet. The worst performance regression is on the ARM Neoverse processor, which we need to investigate more, but it's still in line with a 10% to 15% range given from the Steering Council. So what's next for 3.15, as well as the remainder of the 3.14 release cycle? For 3.15, we plan to spend a bunch of time auditing the standard library for thread safety, especially the less commonly used modules, which we haven't looked at yet. We also hope to have a new stable ABI ready by then, that works with the free threading and default builds of 3.15. That means that CAPI extension authors would only have to build their extension once and can have a wheel that works with both the free-threaded build and the GIL-enabled build. Peter Victorin's working on this. We also plan to improve the documentation. At the Python level, things that are thread safe with the GIL are intended to be thread safe in the free-threaded build as well, with a few exceptions. But the Python documentation often doesn't make it clear what's thread safe or not at all, GIL or no GIL. So that's something we want to improve. Finally, for 3.15 and later, we want to see improved tooling for detecting data races as well as identifying scaling bottlenecks. We have some ideas along these lines, but I think there's still a lot of open questions. Okay, so free threading sounds great. How do you use it? I think by far the easiest way is to use UV. This works on Linux, macOS, and Windows, and has support for both 3.13 as well as the 3.14 beta release. In general, the free-threaded build is indicated by a T suffix. So 3.13T is the 3.13 free-threaded build. You can also install free-threaded Python from official Python installers for Windows and macOS by selecting the appropriate install options. There are also packages for Ubuntu and Fedora. The pyfreethreading.github.io website has install instructions as well as guides for CI and extension authors. Both CI build wheel and GitHub Actions setup Python now support installing free-threaded Python or building free-threaded Python wheels. Finally, in addition to the free-threading Python website, there is now a threading category on the official discuss.python.org forums and an open community-supported free-threaded Python Discord server. The Discord server is great if you have questions about free-threading. There's a lot of knowledgeable people on it. And with that, I want to open it up for questions. Please come up to the mic.
So, hello. 10 to 15% is still pretty substantial. What could you provide? What kind of code would produce the worst case speed reduction with free threading?
What kind of code produces the worst case? I don't know offhand. It's probably some things that heavily access containers that use locking in ways that wouldn't before. Yeah.
Really, thank you for your amazing work. This is incredible. I'm just interested in how this impacts the Python CAPI. Is there anything beyond the critical section changes, and is that also where documentation updates will be made, things like that?
Yeah, so that's a good question. I think the critical section, there's new locks, lightweight locks, that make it easier to make CAPI extensions thread safe. Additionally, there's a few things around reference counting that require new APIs. So for example, because the reference count can be modified concurrently, it's not always safe to check if the reference count is 1 in places where you might use that as an optimization to know that no other thread has access to it. So there's new unstable APIs, so APIs with a PyUnstable prefix to support that sort of thing. Those are listed in the free-threaded porting guide, as well as the what's new for 3.14. Yeah.
Hi. So my question would be: have you experienced in rolling free threading out in a bigger code base? And if yes, what were the implications using rolling this out with extension modules like third-party packages?
So we haven't gotten to the point where we're using it in a large code base yet. We're sort of working on that now. There's a lot of work on extension compatibility. Again, Nathan and Lissandros talk tomorrow. We'll cover that. Sorry, what was the second part of your question?
I think you answered.
Okay, great.
Thank
Thanks. Oh, to answer, sorry, your first question about CAPIs, the other important thing is there are a number of APIs that return borrowed references, and now there are new variants that return. So borrowed references, you get an object, let's say from a collection, you don't increment the reference count. So there are new APIs that return new references. They increment the reference for all the places where we previously returned borrowed references. And that's sometimes important if the collection can be modified concurrently. So examples of that are PyList get item. There's now PyList get item ref, which returns a new reference. PyWeak ref for getting a strong reference for a weak reference. There's similarly one that now returns a strong reference with a reference count incremented. So in general, for thread safety, it's good to use those new APIs.
Thanks for the work. I think it's really exciting. I'm curious, like a lot of the work you're doing seems to be focused on making everything work today the way CPython works. And I'm interested in, can we start moving forward towards like cooperative thread algorithms? So for example, in the C++ world, like stud parallel and MD span and things like this have made it so like your collections can automatically take over your threads and actually be much more faster because you have these threading collectives. I wonder if there's any thought of that, of like redesigning our collectives to be fully threaded collectively.
Yeah, I think that's gotten substantially less. You're right, the primary focus is on basically making Python work today in free threading and make it work generally efficiently, both sort of for single thread stuff and multi-thread stuff. So one limitation here is that for things like collections, like dictionary and list and these sorts of things, they're not really designed to be concurrent collections. And that's partly because the technical trade-offs might mean that they're either very complicated to implement or hurt single thread performance too much. So my take is I think those are better served by other libraries. And so my coworker Alex Turner has been working on an FT utils package. Daniele Parmigiani has been working on another package for concurrent accesses. So that's the kind of thing that I would hope to see in first and third-party packages, and then if needed if they need language support as additional proposals for that.
Thanks for your talk. I'm curious about if you have investigated how free-threaded Python will work with the third-party libraries which use a just-in-time compilation code, and their engine is not a Python but written in some other languages.
So for things like Numba, that might be a better question tomorrow for Nathan and Lysandros. For PyTorch, PyTorch has a sort of it's not a just-in-time compiler for Python code, but it does just-in-time compilation, and there's ongoing work to support that. In practice, I think the challenges there are the same as for other extensions. It's like, how do you adapt to changes in CPython, because CPython APIs change, especially since many of these things rely on internals that change more frequently. But otherwise, I think, at least for PyTorch, it's not, there weren't a whole lot of things that are unique to sort of a JIT compiler.
Thank you.
That's it. All right, thanks everyone, and I'll hand it over to Neil.
Hi, I'm Neil, and I'm here to talk about Pyrefly, which is the Python type checker that we've been writing in beta. If you have any questions, just shove your hand up or come out to the microphone and ask during the thing. Happy to be interrupted. So, first off, what is Pyrefly? It's an open source, standards compliant Python type checker that is also providing an IDE LSP experience, so available in things like VS Code. It is designed to be fast, and it is designed to be parallel. So we heard about how there are all these threads. Let's use them all. And it's from the team that originally brought you Pyre, but it also includes some new team members, for example, who used to work on things like PyType. So a multi group. And it's available at pyrefly.org. So if after this talk you want to go and try Pyrefly for yourself, pyrefly.org will have all the details you need. So let's look at what you get if you try Pyrefly. So this is me using the pyrefly.org/sandbox. So you can try it out before you install it. No installation necessary. Run locally in your browser. You can even try it on your phone if that's all you've got. So this is a little text editor using the Monaco editor that you get in VS Code. And I've typed up a little program. What have I done here? So I've done an import. I've written a little function test that takes an int and formats it as a string. And then I've kind of played around, shoved things in containers, that kind of thing. What's interesting? So I didn't tell, I said that this function takes an int, but I didn't say that the function returns a string. It figured that out for me. And because it figured it out for me, it thought it should tell me, because I might like to know. So it put it in gray for me. If you just double-click that in your IDE, it'll persist into the text. If you don't, that's fine too. It's available for you. It's figured out my local variable y. Looks like a list of string to me. That sounds good. So when I do y square bracket 0 on the last line and pass it to test, I'm giving a string to somewhere I said it should have an int. So it's given me an error. So before I even run this code, it will tell me argument str is not assignable to parameter x with type int in function test. So that's kind of handy, and the little red squiggles. And at the end, I've pressed the dot, and it's told me, this is a str. It's figured out that it returns a str. So OK, capitalize, count, encode, center, all these things are fun and available. If you try Sandbox now, you'll see pretty much this. In the rest of this talk, I'll talk about how we do this, what else we have, what the principles are that we're following, and anything else you might want to know. OK, so you're sold. If you go to pyrefly.org, it explains how to get it. But as simple as pip install Pyrefly and Pyfly init in your project should get you up and running. Or if you go to the VS Code extensions page and search for Pyrefly, should just be one-click install. We were hacking on this morning, so there's a new pip release dropped like, I think, about 40 minutes ago, just in time for this talk, so you can be the first people to try it. And again, pyrefly.org for all the details. So how did we get to Pyrefly? Meta is a large Python user. In particular, we develop Instagram, little app, you may have heard of it. And Instagram is a massive Python code base. And once you're working at Python at that scale, it's really handy to know that when you're making changes, you aren't breaking everything. So you've got to work at a kind of different scale. So in 2017, we started work on Pyre. If you're aware of Meta's other open source projects, we have a project called Hack, which is essentially PHP with types. We have a project called Flow, which is essentially JavaScript with types. And in 2017, we felt the need to do it for Python as well. So we created Pyre, which was Python with types. And like both Hack and Flow, this was written in OCaml and shared a common DNA of common pieces. That was really useful. And to this day, it remains very useful. But it didn't work on Windows. OCaml, it's a great language. I have many friends at Jane Street. There's a lot of work on OCaml, but it's primarily targeted towards more Linux server-side applications, works a bit on Mac. Windows never works quite as well. It did have parallelism, but OCaml didn't have threads, so it had multiprocess and shared memory. As Python developers, pre-free threading, this may seem remarkably common. It works, but it isn't fun, and it doesn't extract the most out of your cores. The performance was a bit lackluster. We don't really know why, might be fair to say, but actually profiling a multi-process OCaml system isn't a fun thing, so I feel we never really figured out why it was slow, but it was slower than it felt it should have been. The IDE wasn't great, and actually we kind of flirted with the idea of an IDE for a bit, but mostly we use Pyrite internally because it's a much better IDE than Pyre. And we released it open source, but we didn't really take it very seriously. If you raised an issue on the Pyre issue tracker, probably deserve an apology from someone. We didn't really take those issues too seriously. For Pyfly, all these 5 things have changed completely. It works on Windows. It is multi-threaded. Performance is phenomenal. It is IDE first, and we are open source first. In fact, we are releasing it to you before we're releasing it internally at Meta. So in August last year, two of us started prototyping MiniPyre. And the idea was, if you're building a type checker from scratch, what would it look like? And so we went through 7 versions of Python type checkers. Not that particularly were very good, but that let us kind of kick the tires on some ideas. So should you use constraints, subsets, abstract interpretation, all these ideas? And eventually we came to one that we thought, this looks good. I like this. It uses Rust, so it is both cross-platform and fast. And we very much started on the hard bits of a Python type checker first. Like type checking, a function call. Well, Python functions are relatively complicated to type check, but we really wanted to go after things like import star, recursion, overloads, generics from the very beginning, because those were the bits we thought might trip us up. And indeed, they did trip up 6 of our prototypes, but not the 7th one. And increasingly, each prototype got better. And so by about October, it was working well. So we decided, we're going to go for it. Decided we'd call it Pyrefly rather than Pyre2, because unfortunately there is Pyre2 library. So started implementing all the features, implementing the spec, packaging it, optimizing it, all these things that you need to do to actually make it real. And then, as of May 2025, here in front of you all, we are releasing it and encouraging everyone to give it a try. Any questions before I continue? Cool. Do feel free to interrupt if you need. So, what are the features of Pyrefly? Well, we think of 4 primary features that we focused on. The first one is performance. We think that type checking should give developers productivity and speed, but if your type checker takes 15 minutes, 10 minutes, even 3 minutes, even maybe 20 seconds to run, it's a trade-off. Like, okay, it would be really nice if I knew if this would crash before I ran it, but actually, probably it's faster if I just run it. So, now you're always making the trade-off, what do I want to do? However, if your type checker is super, super, super fast, you don't have to make that trade-off. You can just run it. You can just have it always going in the background. So Pyrefly is designed with the idea that it would check on every single keystroke in VS Code. And we can currently do, on large code bases, about 1.8 million lines per second. So if your Python code base is not measured in millions of lines, probably it won't take very long. And we are 35 times faster than Pyre1 on Instagram, and 14 times faster than both MyPy and Pyrite. I think it's 14 times faster than Pyrite, and then quite a lot faster than that than MyPy for PyTorch. And that was on a 10-core MacBook. Give us more cores, and the delta gets much larger. All the details of these benchmarks are on our website at pyrefly.org, so you can try it out yourself and see how you find it. The advantage of working with Rust is that Rust is fairly fast as a default. It has optimized memory representations. You control where the allocation goes. You can do things like lifetimes. So that's nice. And then on top of that, you add parallelism. So we use module-level parallelism. So basically, every file in your project, we will check on a separate thread. The kind of most files take, kind of in the 200 milliseconds or less range to check. So then you throw lots of cores at it, and it doesn't take very long at all. And then for even larger projects, we have some very important incrementality features. So if you change a key, if you add a character in this file, and it doesn't impact the rest of your project, we won't check the rest of your project. So this gets us kind of like under 100 milliseconds in most cases, even with cyclic imports, and that's on the very large projects we test on. The other thing about performance is we have to continually be fighting the n-squared monsters. It's very easy to design a type checker, and accidentally everything in the type checker kind of wants to be n-squared if you do it in the naive way. So we're always benchmarking, always looking for those n-squared, and then fixing them. But that's probably most of the work for performance. I see Gia nodding his head. He's got some battle stories. The next feature we wanted to really double down on was inference. I'm a Haskell programmer. I did over a decade of Haskell, so I love types. But that's not where the Python community is, and not necessarily where they should be. Different languages for different purposes. So we want Pyrefly to meet you where you are. It should give you types and give you the benefit of types, even if you don't particularly care about them. So it's designed to infer function return types, local types, and container types. So if you see, going back to the example at the beginning, it infers that this returns a string. It infers that the container must be used as a list of string. It just kind of all works out, and then it kind of does everything else. And then it also tells you what it inferred. So if it ever gets a mismatch, you can see its thought process, really. The next feature was the IDE. For Pyre, we designed a static type checker on the command line and then tried to shoehorn an IDE in. That isn't the right way to do it. The right way to do it is to design an IDE and then run it on the command line, which is exactly what we did. So there's features like an in-memory transactional state database, so you can have one state of the code, and then if you do an operation like find references concurrently with the go-to definition, on a really large project, find references might take you a few seconds. Go-to definition, you still want to be kind of 10 millisecond mark. So you can do both in parallel without blocking or anything like that. We've got a VS Code extension, and if you do Pyfly LSP, it spawns up an LSP server. So people have plugged this into NeoVim. If you use the VS Code extension, it will download a bundled copy of Pyfly as well, so it should just work out the box. We've got all the usuals: hover, go-to definition, completion, find ref, document symbols, ... Not quite everything you would expect in a fully featured LSP yet. No refactoring, a few things like that missing, but they're on the plan. Type inference, as before, like I talked about inference, I talked about performance, and they're really both coming together for the IDE, because you have the type inference and then the inlay hints, which are those little gray words. And then finally, perhaps the most important feature, open source. We, the team, and Meta as a whole have gained so much from open source. Like Python is open source. The Python typing specification is open source. The existing checkers like Pyrite, MyPy are open source. The rough parser from the formatter from Astral that we use is also open source. We have built on open source, and we kind of feel it's important that we contribute back to open source and run this like an open source project, encouraging contributions, encouraging reports, responding to issues, that kind of thing. So all the code is on Facebook/Pyrefly. It's under the MIT license, so very standard Python. And last week, we got 6 pull requests, very happy about that, of which we accepted 5, and one was a documentation change where actually we helped the user figure out their problem, which was a problem with their system, not the documentation. So that was all the pull requests. Hopefully this week, from the people in this room, we're going to get many more pull requests than that, and we'll be accepting them all. We're delighted to accept them. We're running at about 200 to 250 commits a week. Although this morning was pretty frantic, trying to push in last-minute fixes, so I suspect we're well over that this morning. So stepping back, we've written a Python type checker, but isn't Python untyped? I mean, yes, but no. The way I think of it is, at runtime, Python does have types. So if you have a str and you pass it to where you wanted an int, it will blow up. For developers, you might not have types, but you have an idea of the intended meaning of a variable. This is a user ID, however it is. If those don't agree, your program will not have a good time. And so types, I think, are the way you connect those two domains, what you think and what the machine thinks, and hopefully not blow up in the process. And once you've adopted types, I think there are a number of benefits you get from this. So firstly, you need to run the code less. Rather than running the code to find a type error, you can get the type error in the IDE, and it will stop you and alert you in advance. You can spot typos. If you've got a class and you do field name and the field name is spelt wrong, it will tell you. And I've done this in my Python programming. I don't have great sense of spelling, so this is great for me. The other thing I often find is like my exception handlers, the chances of me getting writing an exception handler that crashes when executing are fairly high. And it's not the kind of code you ever test. So types can give you just some level of safety that your exception handler and these kind of less tested pieces of programs are likely to do something not entirely stupid. You can also write code faster with autocomplete. That's a game changer. It also kind of gives you machine check documentation and finally lets you kind of refactor freely with some peace of mind. Take, for example, this code. This is some code I pulled out of I think I found it on the web, actually, with names slightly changed. This code really doesn't make all that much sense if you don't have the types. But with the types, I can kind of understand what it's doing. It's kind of processing date time stuff into a bool of float or an int. And then this my list over here is processing it to filter out the ones that are not bools. And so actually, from this, I can tell that my list is probably some timestamps in some system. And now you can kind of start to get a feel for it. Whereas if you just read the code, it's kind of hard to grok on its own. So I find this kind of interesting where like types, even though we haven't actually written any types in this system, can be useful to understand how it works. So types are there for reliability, code crash less, productivity, write your code faster, understanding, so you can understand the code, but this isn't a kind of like everything should be typed everywhere. It's only where it makes sense. So do we need Kleisli arrows to describe our functions? Probably not. If it feels like you're going off the deep end, just shove an any in there. It's not the end of the world. The idea of Python is that we can get some of the benefits of types, in fact, most of the benefits of types, without necessarily committing to a maximalist approach that other languages do. Works for other languages, but probably not what we're looking for. So hopefully keep Python simple. OK, so I'm going to talk a little bit about the design of Pyrefly, because I thought that might be fun. But if you're looking for more details, Stephen Troxler is giving a talk tomorrow at the Typing Summit that you're all invited to, where he'll go through this in much more detail. So Pyfly works as 3 phases, so where each phase is about 10 times more expensive than the last. So in the first phase, we look through a module's exports. What does it import? What does it export? What will other modules be able to get from it? So for example, we might discover that module foo exports built-ins.str and my class that it defines itself. In particular, the import star thing is the kind of thing you need to resolve here, which can be surprisingly tricksy, especially if it's in a recursive fixed point with itself, which some people do. The next phase is the bindings phase. So how do statements relate to each other? The idea here is where you've written x equals something, and where later you've used x. Those two x's are related. If there's flow control, how does the flow control modify which variables in scope? Where are variables coming from? Where are they going to? This kind of deals at the statement level. And then the final phase we have is answers, where given that we've broken these statements down into just bindings, how do the expressions and the types relate? So for example, given a sub-expression, an expression and the types of all the sub-expressions, what would be the resulting type? So for example, I might know that x is a list of string, 4 is the literal 4. What is x.pop4? The answer in this case would be str or none. So it's that kind of thing. I also wanted to kind of draw back, like, what does Pyrefly do? Well, one of the things it does a lot is autocomplete. And let's imagine we've written display 3.142 fraction dot. We now need to generate a list of autocomplete. how might we go about that? Well, so the first thing we need to do is find the type of the display 3.142.fraction expression, which requires us to first know what we're talking about. So we need to know which display function we're using. So if we've got the imports of typing and numbers, then it might come from typing, it might come from numbers. So figure out what the exports of each are, might require fixed points of the recursive star imports, and figure out where it comes from. Very much the export phase. Please? That was, how do we get the VS Code extension to know what version environment we're in? We have a config.toml file, a pyproject.toml file, where you can tell it, I'm in this version, this is my site path, this is my search path. You can also tell it, this is my interpreter, like python.exe, Python 3, whatever. And then we will go and ask Python, what is your version, and that. And then if you have nothing, we will assume that it is the Python on your path, and we will go ask it. So you can configure it, and if you configure it, you'll get very good results, but hopefully out the box, you'll get reasonable results, depending how non-standard you are. If you're having trouble configuring Pyrefly, do please open an issue on the GitHub or go to the Discord on our Pyrefly website, where we'd be happy to help.
We also look in the VS Code setting. So like in VS Code Informer, if you set it, which could be different for different users.
To repeat that for the thing, we also look in the VS Code settings. Finding your files and finding your projects is actually one of the hardest things. So figuring out that numbers and numbers.py are the same thing, remarkably tricksy. And perhaps the hardest thing is when you've opened a file numbers.py, knowing that it is the numbers module and not the, say, foo.numbers module, again, is remarkably tricksy. These aren't the fun problems, though, so I left them out of the slides, but maybe that was a mistake. So we found display, and this is the source code. It is a function that takes a float, and the bit in gray is what the type checker has inferred. So you'll see we've had to infer some local variables, understand the flow control, instantiate some generics, understand the data class modifier, understand final, and after all that, we can kind of guess that display will return a number float, which means we're now slightly on our way to understanding what the type of dot fraction might be of that. And then finally, now we know we have a float, we have to figure out what methods it has, which for float has no inheritance, but for some things, inheritance, MRO, it's a lot of stuff. And in fact, as I looked at this morning, I do not think fromHex should be on here because it's a class method, not a variable method, so we should probably fix that. But yes, as we said, there's a lot of work to do, very easy to get it wrong. I have proof. And now we can display very prettily all these completions. Ooh, didn't load this load. Try reloading. Never seen that before. Show anyway. OK, it has lost all my pictures. That is frustrating. OK, I will talk through what is on this slide. So on this slide, there is a picture of the Pyrefly team, who happily is also at the back here. So give a wave. We're all in these T-shirts. So if you have any questions about Pyrefly, come to one of us. There are also pictures of these stickers. So if you try out Pyrefly, start the GitHub issue, install the VS Code extension or anything, come grab us for a sticker. There is also a picture of the very lovely Meta booth, open source booth. I think we are first on the right as you go into the convention hall. On Saturday and Sunday, my understanding is we will be serving coffee as well. And there will also be a demonstration of Pyrefly, and people around who can help you get it set up. Yeah. We are also around for the rest of the conference, but also at the Typing Summit tomorrow, which is 2 till 6 in room 319, which is just a few doors down. No pre-registration, so everyone is welcome. We'll be giving a number of talks there. So Stephen will be talking about introducing Pyrefly, so a demo of the stages of how Pyrefly works. Gia and Amrita will be talking about PyRead-only, how you can reduce unwanted mutation. And then Rebecca Chen will be leading the updates from the Python Council as part of her work. So please do come join us, and also come reach out to us as you're going around. Any questions? Oh, if you could light up on the mic so that everyone can hear you. You're first.
Great. So let's say that I'm a guy who really likes types. I also have a history with Haskell. And my coworker is the kind of person who, for some reason, prefers writing code over types. What is the minimum that I need him to do in order to make my experience with Pyrefly great? And in turn, as a follow-on to that, can I make Pyrefly yell at him for not doing it?
Can you make him yell at you? No, not at the moment, but we may have more restrictive. So Pyre has a strict mode which requires types in more places. We are likely to introduce something like that. What's the minimum they need to do? Probably nothing. Probably just, Pyrefly is designed, if you add types and they introduce a type error, they'll get an error for it. So as you gradually type your code, you'll probably be able to gradually bring them along. Hopefully, it will show them their errors before they land them, and then they'll change their mind. That would be the ideal. But yeah, it shouldn't require anything. Presumably, you want to put it in your CI. Giving them the VS Code extension is probably a nice thing to do. But yeah, shouldn't be anything too much.
Excellent, thank you.
You mentioned about generics in the first few slides. How does Pyfly handle covariance?
So at the moment, we don't have variance inference, but that is on our list of things to do.
Awesome.
But we do have, with type var, it's standard to write the variant, covariant, invariant annotations. We deal with that. I mean, so the core piece of Pyrefly is essentially a subset check, where is this type a subset of this type? For covariant, you flip them. For invariant, you check them both ways. And for contravariant, you just keep them where they were. So it all just kind of falls out from the subset and approach.
Sounds good. Do you have a spoiler and when you're considering release those?
So it is released now, and you can use it now. We are give it a go. We wouldn't consider it production ready, but it may be not too far off. We're aiming for a V1 that is kind of like where we would say, like, yes, everyone should use this. But even now, like one of the slides you missed was my son doing his homework. Let me see if I can get this. My son does his homework using Pyrefly. So where is it? Yeah. This is my son doing his homework with Pyrefly. So it's good enough that my son can use it. He is 12, so he's probably not doing it to the level you are doing. He's definitely not doing free-threaded Python, but it is usable, and I will inflict it on my child.
Great.
Which maybe tells you more about me than Pyrefly.
Alrighty, number one, super excited to see new open source development in the Python type checking kind of area. Two quick questions. Number one, I know that Astro, the team behind Rust and UV, they're also releasing their own Rust-based Python type checker. I believe it's called TY.
Yep.
Just want to know the team's opinion on it. Have you tried it? What are pros and cons between each of the two right now?
We have tried it. We have opinions. I suspect the best thing is that rather than we tell you what we think, you try it for yourself and see what you think. It's all open source. It's all public. So, yeah. But we very much respect their work, especially around UV and Rough. And we use their same parser, which is phenomenal. So, yeah, they're a great team.
For sure. And I actually have a follow-up question about that. One interesting thing about TY is that they use Salsa, which is a Rust-based incremental engine that I believe Rust Analyzer also uses. And I read the README for Pyrefly, and they specifically mentioned it. The reason why you guys don't use it is because you guys wanted module-level incrementation instead of more specific fine-grained one. Just curious, why is that, and kind of what are the decisions behind that?
So, I mean, the team from Meta that works on Rust Analyzer, they are also part of the team developing Salsa. So we spoke to the Salsa developers extensively before we started. So Salsa makes a number of decisions about the granularity at which you work. It imposes a cost on every operation. So we very much wanted to have our type checker. Salsa is great if you are great at Rust. If you are a Rust beginner, it complicates and kind of you have to thread it through every sub-expression transformation. We didn't want that. We want it to be more approachable to beginner Rust programmers, very deliberately. Most of our team learnt Rust on this project. Salsa also, its mechanism of cutting recursion, well, I mean, it had no mechanism of cutting recursion. Astral added it. I think that the one we have is better. It uses a fixed point with a base assumption. It's encoded in recursion, so it is both less invasive for the rest of the code, but also more performant. The other thing is we check at the module level. This is somewhere we diverge from somewhere like Pyrite. So Pyrite does outside-in, like the C# type checker. We deliberately say, if we're going to check something, we're going to check the whole module, and we're going to make it super, super fast to do that. And like our P99 is like 20 milliseconds or something. So it's like go very, very, very fast on a single module. And then that can be our level of granularity, which then reduces the memory overhead, especially as you get to really large projects. So we certainly considered it in depth. I'm happy to talk more, because I spoke for hours with the Salsa developers before we started.
Awesome. Thank you very much.
No problem.
Congrats on getting this out. It seems really cool. I was curious, what's left before you can fully roll it out in a large organization?
We are rolling it out in a larger organization as we speak. For larger organizations, there's a lot of things around, comparability to existing type checkers. So like where we've got Pyre rolled out, we need it to be approximately the same as Pyre. In some cases, Pyre is wrong. In some cases, Pyre is right, and it's kind of, run down the divergence list to the point where it doesn't matter. There's also things like logging, telemetry, upgrades, which are not very important on a small scale, but on a large scale, they're kind of all that matters.
So you mentioned like the variance inference is one thing. Are there like large things in the type checking that are still to do?
Yes, I mean, so if you go to our GitHub, there's a milestone for V1, variance inference, recursive type alias. There are a handful of these. I think we'd like to improve our overload resolution a little bit, but it mostly works for most projects. And what we're working on at the moment, there are, I think, like 6 kind of big-ish projects, but mostly it's there.
Cool, thank you.
Just wanted to echo the congrats. I would notice playing around that you guys support what I would describe as type aliases nested in classes or like associated types.
Yep.
I also noticed that there doesn't seem to be any kind of intersection type support. I was wondering if you plan to like clearly delineate where your philosophy differs now that there's like a proliferation of other type checkers like TY and MyPy.
So there are a lot of places where the typing spec isn't particularly precise. Like it kind of implies flow types, but doesn't explicitly say it. One of the reasons we work with the Typing Council, and we're at the Typing Summit tomorrow, is to try and nail down some of these things. We have intersection types, but we don't particularly use them. We don't generate them in most cases. It would be really good to get kind of a decision from the Python community as a whole. Like, do we want to make them first class? In which case, we'll double down, and things like narrowing we'll do through them. Or do we want to kind of back away from them? In which case, we'll do other things. And things like, should type aliases be allowed in classes? I would rather everyone follow the same answer. I don't think we particularly thought too hard about that one. It just kind of fell out.
Yeah, exactly.
But yeah, we would rather there was an answer. So Eric Trout's work on the conformance test suite has been phenomenal. We are using that as part of our kind of like divergence mismatch. And yeah, long may it continue.
Thank you so much.
All right, so we have like 6 type checkers now, or so to say. So if I'm a library developer, how do I make sure that my users get the good experience independent what they use? And slightly related to that, is there any features of Pyrefly that you'd like to standardize? Like, I don't know, like for example, the gradual type annotations or what? Inference or whatnot?
It would be nice if they all work the same. So I think for areas like inference, if you explicitly give type signatures to your exports, that will give users the best experience. And as soon as you're giving explicit type signatures, the type checkers may disagree about what warnings they give to you, but hopefully they won't disagree about what warnings they give to your users. So full annotations on all exported things. Something like Pyrefly might be a way to get there because it will infer things and help you write them out. My hope is this won't become a problem, but I can totally understand why it might. So I think this is probably something the Typing Council should be thinking hard about. Because, yeah, we don't want to increase the work for maintainers. That would be bad.
All right.
Hi, thank you for the presentation. You said in one slide that, explain what the open source aspect and you wanted to give back to the community. That sounds really nice, but I do understand that having an open source project that interacts with being genuinely open source, interacting with the open source developers, that costs a lot. Yeah. And I was wondering how you were able to convince the Meta leadership, and if you needed to go through this process of making this truly open source, well, what is the strategic benefit out of all of this?
So, I mean, Meta has loads of open source projects, something like PyTorch, which is owned by the PyTorch Foundation. It has a substantial number of Meta developers. They don't work on, that is GitHub first. It is an open source project that would use something like Pyrefly as an open source project. So while for most internal languages, we don't use it open source, we don't put our code open source, for something like Python, actually a reasonable amount of our code, especially the AI research, the SegmentMe, all these things coming out, they are done in the open on GitHub. So we are helping them as well as the open source community. Mm-hmm. There is value to the open source community. I think we made that argument because Python is so open source first. But we have internal value too, which makes me slightly less worried that it'll ever change.
Okay, thank you very much.
Hi, thanks for taking so many questions. I'll try to keep it brief. There's another project in this space that some people in the room may have heard of called TypeScript.
Yep.
Two of my frustrations with that one are the sometimes indecipherable error messages and the type instantiation is excessively deep issue. Does your team have any thoughts on how to address or prevent those?
So for error messages, we've worked somewhat on error messages. They're probably not as good as they need to be, but they're definitely better than they were when we started. Error messages, it tends to be an effort thing. Mm-hmm. We have a large number of Python developers. We would rather be developing Pyrefly than answering their support questions of what does this mean? So hopefully we're aligned there. Not sure what you mean by the deep instantiation.
Oh, that's all right. Don't worry about it.
Cool. You can grab me after. We can talk about it.
Thank you.
We have reached time, but I'm happy to take questions basically all night. So feel free to leave if you want, or feel free to listen, or feel free to ask.
Yeah, I'm just curious about the overlap with Monkey Type as an open source project. I'm wondering whether there's any implementation overlap and how you're able to use runtime to then generate.
Yeah. We don't currently go near runtime, and we don't have the generation.
Okay.
It's probably how you type an untyped code base is something we will definitely be looking at in the future.
Oh, okay.
And something like Monkey Type might be great for that.
Yeah.
But not yet.
Okay, cool. Thank you.
I have two quick questions. So are you planning to build an extension for Z editor?
We would love, so some of our team are big Z enthusiasts. We would love to, ideally, with help from the community. Z doesn't do the JavaScript, but it does do LSP, I think. Or
yeah, it does LSP.
Yeah. So we do LSP, standard LSP. If you do Pyfly LSP, you get a full LSP. So how do you write the extensions for Z? Is it in the Rust?
Yeah.
Yeah.
In Rust.
So someone would have to mirror what is in our TypeScript extension into the Rust. we deliberately put as little as possible in our TypeScript extension, so it shouldn't really be very hard.
Oh, okay. And the second question is, I could not hear what, maybe you have mentioned it already, how Pyrefly works with the algebraic data types.
Algebraic data types?
I mean, it's the union and the sum types and product.
Yeah. I mean, so class, it works with fine. Union, it works with fine. So it basically has full coverage of algebraic data types. And it has things like match and everything. So you should basically everything's there. That way.
Thank you.
Cool. I will turn this off. Thank you very much.